Our sun is a magnificent celestial body. It is a giant ball of plasma, not a solid object. Deep within its core, a nuclear furnace rages, fusing hydrogen into helium and releasing tremendous energy. This energy doesn't stay trapped, it radiates outward, bathing our solar system in light and warmth. But the sun isn't just a passive energy source. It has a dynamic personality, driven by its powerful magnetic field. This field originates deep within the sun. Electrically charged gases churn and flow, creating this invisible force. Unlike Earth's relatively stable magnetic field, the sun's is constantly changing. It twists, it turns, and every 11 years or so it flips completely. This magnetic flip is a reminder of the sun's awesome power. It is a phenomenon that has captivated scientists for centuries. Understanding the sun's magnetic field is crucial. It directly influences space weather. It can impact our planet in significant ways. Deep within the sun, a fascinating process unfolds. We call it the solar dynamo. This dynamo is responsible for generating the sun's magnetic field. It operates in the sun's convective zone, a region of turbulent plasma flows. Imagine a boiling pot of water with hot plasma rising and cooler plasma sinking. This constant churning combined with the sun's rotation creates electric currents. These currents, in turn, generate the sun's magnetic field. The sun's rotation is not uniform. The equator spins faster than the poles. This differential rotation stretches and twists the magnetic field lines. Over time, these lines become increasingly tangled and energized. They build up tension, like a rubber band stretched too far. Eventually, this tension reaches a breaking point. The magnetic field lines snap and reconnect in a new configuration. This is the solar magnetic flip. The sun's magnetic field doesn't flip overnight. It goes through a cycle, a rhythmic ebb and flow of activity. This solar cycle lasts approximately 11 years. It is characterized by periods of relative calm and periods of intense activity. The cycle begins with a solar minimum. During this time, the sun is relatively quiet. Sunspots, those dark blemishes on the sun's surface, are few and far between. Solar flares and coronal mass ejections, powerful bursts of energy from the sun, are less frequent. As the cycle progresses, solar activity increases. The sun awakens from its slumber. Sunspots become more numerous. They often appear in groups and can be larger than Earth itself. Solar flares and CMEs become more common, releasing tremendous energy into space. The peak of the solar cycle is called solar maximum. During this time, the sun is at its most active. Sunspots are abundant and solar storms are more likely. The sun's magnetic field is on the verge of flipping. After solar maximum, activity gradually declines. The cycle begins anew, heading towards another solar minimum. Sunspots are more than just dark spots on the sun. They are visible manifestations of the sun's intense magnetic activity. These blemishes appear darker because they are cooler than the surrounding photosphere, the sun's visible surface. Sunspots form when magnetic field lines become twisted and concentrated, inhibiting the normal flow of heat from the sun's interior. Imagine these magnetic field lines as kinks in a hose. These kinks restrict the flow of energy, causing the region to cool and appear darker. Sunspots are often associated with solar flares and coronal mass ejections. The larger and more complex a sunspot group, the higher the likelihood of these powerful events. By monitoring sunspot activity, scientists can gain valuable insights into the sun's magnetic field and its potential to impact Earth. Section 5. Solar flares and CMEs, eruptions from the solar forge. Solar flares and coronal mass ejections, or CMEs, are the sun's most powerful displays of energy. These eruptions release immense amounts of radiation and charged particles into space, sometimes directed towards Earth. Solar flares are sudden, intense bursts of radiation. Think of them as massive explosions on the sun's surface. They emit X-rays and ultraviolet radiation that can travel at the speed of light, reaching Earth in a matter of minutes. Solar flares can disrupt radio communications and pose risks to astronauts and satellites. CMEs, on the other hand, are massive eruptions of solar material. These eruptions hurl billions of tons of charged particles into space at high speeds. Imagine a giant cannon on the sun, firing a cloud of plasma into the solar system. When directed towards Earth, CMEs can trigger geomagnetic storms, disrupting power grids, satellite operations, and creating stunning auroras. Section 6. The Carrington Event, a glimpse into the sun's power. In 1859, the world witnessed the most powerful geomagnetic storm ever recorded, the Carrington Event. This event, triggered by a massive solar flare and CME, serves as a stark reminder of the sun's potential to disrupt life on Earth. During the Carrington Event, telegraph systems, the primary means of long-distance communication at the time, went haywire. Operators received electric shocks, sparks flew from equipment, some telegraph stations even caught fire. Auroras, usually confined to polar regions, were visible as far south as the Caribbean and Hawaii. Today, our world is far more reliant on technology. A Carrington-scale event could have far more devastating consequences. Power grids could experience widespread blackouts. Satellites could be damaged or destroyed. Communication systems could be severely disrupted. The economic and societal impacts would be significant. Section 7. Predicting the flip scientists as solar detectives. Scientists are constantly monitoring the sun. They use sophisticated instruments both on Earth and in space. They are like detectives looking for clues to the sun's next move. Their goal is to predict solar flares, CMEs, and the timing of the sun's magnetic flip. They track changes in the sun's magnetic field. They observe sunspot activity. They monitor solar flares and CMEs. They use this information to develop models and forecasts. These forecasts help us prepare for potential space weather impacts. One of the key tools in their arsenal is the Solar Dynamics Observatory, or SDO. This space telescope captures high-resolution images of the sun. It measures its magnetic field strength. It detects solar flares and CMEs. The data from SDO and other observatories around the world provide valuable insights into the sun's behavior. Section 8. Shielding our world, preparing for the solar storm. As we approach the peak of the current solar cycle, we must be prepared for the increased likelihood of solar storms. Governments, space agencies, and private companies are working together. Their goal is to mitigate the risks associated with space weather. One crucial aspect is improving space weather forecasting. By enhancing our ability to predict solar flares and CMEs, we can provide timely warnings to critical infrastructure operators. This includes power grid operators, satellite operators, and aviation authorities. Another important aspect is hardening critical infrastructure against the effects of geomagnetic storms. This involves designing systems that are less susceptible to voltage fluctuations. It means developing backup systems to ensure continuity of service. Section 9. Technological resilience. Fortifying our systems. Our technological reliance makes us vulnerable to space weather. We must take steps to make our systems more resilient. One approach is to design equipment that is less susceptible to electromagnetic interference. For example, power grids can be designed with safeguards to prevent widespread blackouts during geomagnetic storms. Satellites can be equipped with radiation hardening to protect them from the damaging effects of solar flares. Communication systems can be designed with redundancy to ensure continuity of service. By investing in technological resilience, we can minimize the impact of space weather on our daily lives. We can protect our critical infrastructure and maintain essential services. Section 10. Public awareness, knowledge as our shield. Public awareness is crucial. When people understand the risks of space weather, they can take steps to protect themselves and their families. Governments and space agencies play a vital role in educating the public. They can provide information on space weather forecasts, potential impacts, and safety precautions. During a solar storm, it is important to stay informed. Follow official guidance from authorities. Be prepared for potential power outages and communication disruptions. By staying informed and taking appropriate precautions, we can weather the solar storm together. Section 11. Conclusion. Embracing the sun's rhythms. The sun is a source of life. It is also a source of potential disruption. By understanding its rhythms, its cycles, and its power, we can better prepare for the challenges of space weather. The upcoming solar magnetic flip is a reminder of the dynamic nature of our universe. It is an opportunity to appreciate the awesome power of our sun. It is a call to action to invest in research, preparedness, and mitigation. By working together, we can harness the sun's energy while safeguarding our technological civilization. We can ensure a brighter future for all.
So hit that subscribe button, ring the bell for notifications, and let's turn the page on a new adventure together. Get ready to experience books like never before, only on VBook 360. Like, comment, and share to support the channel and keep the video magic alive. Thank you for stopping by. And remember, every video has a story, and every story deserves to be shared. See you in the next video.